So let's go over Chapter 6 in the Grossman, the Art of Writing Reasonable Organic Mechanisms, the problems we actually worked on these in class. So 16 total of these. The first one is 6.1. So this involves platinum 0 here. Platinum 0. 6.1. We have this B pin, so a diboron bond. That is the most polarizable bond, weakest bond. So that's where we're going to do an oxidative addition actually is in that bond. So our platinum 0 is pretty nucleophilic, right? So it does have a lone pair, so we do our whole fishhook arrow mechanism, oxidative addition. Also in the system is an alkyne. Right? The alkyne coordinates to the platinum 2, right? And now the platinum 2 is pretty strongly electrophilic. It's going to do a migratory insertion, so one of the ligands on the platinum, one of the B pins is going to migrate. Somebody could have a good question. How do you know which one's going to migrate first? Because technically this carbon right here and this carbon right here are different, right? Actually, you don't know. So I just chose to have it go to this carbon. So really, in reality, it could have gone to either first. Been fine. Either first would have been fine. Then we do our migratory insertion, do a reductive elimination, and we get to our cis addition, right? We had things cis in metals because of the alkyne cis addition, and we're back to platinum 0, so we can restart the catalytic cycle. All right, going on to 6.2. 6.2, again, now we have rhodium 1. Right? We want to look for the most polarizable bond for the oxidative addition, and in this case, that's going to be the silicon H bond. Right, silicon H bonds, we do oxidative addition. We coordinate then to to a ketone. I usually don't show the coordination step. You don't need to say something coordinates. All of a sudden it can just show up. That's what I usually do. The book sometimes will say coordination, and then you have to redraw it. You don't have to redraw it in coordination.
I feel like coordination and insertion in the same step. Like write coordination / insertion.
Yeah, you could do it in the same step. That's, yeah, sure. Yeah, that's fine. So then here in this case, in this problem specifically, they're asking you to show the migratory insertion a different way. I think in the book they showed the silicon migrating first, and this time they said we'll show the H migrating, right? Because again, it doesn't really matter which ligand migrates first because the product's gonna be the same either way. So here we're showing the H migrate to the carbon of the carbonyl, pi bond coming up. So migratory insertion, of course, we do not change oxidation states in migratory insertions. So it's still rhodium 3, right? We do reductive elimination, get back to rhodium 1, and right, if this was in a ring, you'd see that right these have to be a cis addition, right? It has to be a cis addition. So back to rhodium 1, and that's that one. So now we're going to 6.3 again here. Right, we got to identify the most polar bond. If we're going to do any oxidative addition, we got to find the most polar bond. And in this case, it's the Si, the silicon H bond. Again, with most of these, you're given the product. And so when you look at the product, you say, well, what bond? Like, so here's the final product. What bond is not there anymore? The silicon H bond. So that's one of the things. Right? How do I know that's the one? The other thing you do is look at the product and say, well, what bonds have broken? What bonds have changed? Right? And all of a sudden, there's no silicon H bond, so that might be the spot oxidative addition takes place just by noticing in the product afterwards, right? They probably wouldn't be able to predict this beforehand. So oxidative addition, rhodium 1 goes to rhodium 3. Then at this point, migratory insertion takes place. This you gotta be careful. This is something at this point it's tough to kind of realize, but with just carbon cycles, what's the preferred size of a ring for carbon? 6. But if you drop a silicon in there and an oxygen, which are bigger elements, the preferred size becomes a little less. It becomes 5. Also, it's tough, right? So it does migratory insertion in forms of 5-membered ring. It would also be tough for the rhodium to be inside the ring, right? Because then it's kind of in the way versus being on the outside the ring. So they call this a exocyclic versus if it attacked the N carbon to be an endocyclic reaction. There's a whole set of rules called Baldwin's rules that helps us understand which types of cyclization reactions are possible. But in this case, 5-member ring's better, silicon's bigger element. Also, it keeps the rhodium kind of away sterically instead of having it, right, if this was here, the rhodium would be there and it might be in the way, like a 6-member ring, some sort of axial or equatorial position. So the rhodium's out here. Coordination, there's CO in this system, so carbon monoxide is going to coordinate to the rhodium. And at this point, we're going to do another migratory insertion. Right, you could have done the migratory insertion of the H coming first. That's fine. Right, you could have done the H coming first. Right, usually you don't. Usually the carbon bond gets made first, but you certainly could do the H getting made first here. Right, so the electrons here attack the carbon of the carbon monoxide. Pi electrons come down. That forms now a real bond with rhodium. Still rhodium-3, right? Migratory insertion. We do a reductive elimination. Make the aldehyde and regenerate rhodium-1. Yeah, I forgot to say, right, there was another coordination here. That's a coordination bond. So this alkene pi bond is coordinated to the rhodium here as well, which helps facilitate the migratory insertion. All right, taking a look at 6.9. This is a little different here. Now we have mercury 2. And what you have here is you have an alcohol, an alkene, and an aldehyde. So here, there actually is no really good polar bond to do an oxidative addition. Right? So there's no place to do an oxidative addition. Right? And OH is not quite the same as a silicon H. And there's no carbon iodide. There's no carbonyl triflate. So in this case, also you should hopefully recognize an aldehyde and an alcohol will actually react like in an acid-base kind of chemistry sense. I could have drawn the mercury serving as just a Lewis acid here to make this aldehyde that much more reactive, right? So the oxygen attacks. Yes, so we form, right, a tetrahedral intermediate. Do a proton transfer. So this first couple steps have nothing to do with organometallics in any way, shape, or form. It's just basic carbonyl chemistry. Right, proton transfer. Now we have what we call an acetal. Right, an acetal there. There's a carbon that was an aldehyde. See a lot of times in sugar chemistry. Now the mercury can come into play. Right, again, you knew the product. They showed you the product here. And most of these mechanisms that I would give you, you have the product given to you. Right, so it's harder if you don't know what the product is. It's a lot harder to draw these. But if you're given the product, you can usually logically find your way there. So, right, so they were given the product, so we could have gone back and done. Right, they were given this bonds broken, bonds formed, all those things.
Isn't this how we protect?
Yep. So it's one way to protect, right, an aldehyde in some sense, kind of, right. So now the mercury coordinates to the pi bond of the alkene. This oxygen attacks that carbon. Now a 6-member ring is fine because now there's not silicon. Again, it's nice because we put the mercury on the outside, right? Mercury didn't change oxidation states. It's really more like just a ligand substitution, right? You're forming a carbon-mercury bond and kicking out the L-acetate.
To form the anti-Markovnikov?
Sure, it's anti-Markovnikov. It's not really Markovnikov and anti-Markovnikov type of thing here.
Yeah.
It's not. That's a little different. So it's not really that kind of thing. O-acetate comes back in, takes off the H, make another acetic acid, just an acid-base reaction, and that gets us to our product, where we have mercury 2. So this is not a catalytic process. The mercury actually ends up in the final product, so it's not catalytic. Right, that's the other clue. When you see the mercury, the metal in the product, it's not catalytic. All right, continuing on, 6.10. Now here you have palladium 2, and then one of the good questions is, how do I know if I want to turn palladium 2 into palladium 0? So one of the things you want to look for, usually oxidative addition is easier for palladium 0, but if you look at this substrate in 6.10, again, there are no really polar bonds, right? There aren't those carbon iodide, carbon triflate, places that do oxidative addition. So that's one of the ways you know it's okay to stay with palladium 2. So palladium 2 by itself is a really good Lewis acid. It's pretty electrophilic, so it's going to want to coordinate to an alkyne. Right, an alkyne is electron rich. Palladium 2 is pretty delta plus. So what can happen here is essentially a ligand substitution, right, where the oxygen attacks the carbon, electrons from the pi bond go to the palladium and kick out a chlorine. So it's like a ligand substitution here. So palladium still stays palladium 0, right? We form a 5-member ring. Palladium's in the ring, which isn't great. But we're not going to form 4-membered ring, right? That's not going to happen. The angles for a benzene ring just wouldn't be possible. Plus, it wouldn't be aromatic, right? If you look at our final product, we're making an aromatic product, so we know, again, which bonds we want to make and break. So now you have palladium-2, you made Cl minus the OH, so we'll make some HCl. That's just some acid-base chemistry. And this is simply one way you could have done this. You could have done this other ways, right? You could have just said, if you wanted to make this quick and easy, you could have said these 2 electrons here are just going to take the HCl, right? You kick out the Cl minus, you have palladium plus Cl minus. You could do it that way, right? Eventually you need to get back to palladium-2 chloride. But one way you could do it is have the pi bond attack. You'd form a really stable carbocation, right? And now the Cl minus can come back around, attack the palladium, kick those electrons down. It's like another ligand substitution essentially as well. Get back to your product and get back to palladium-2. Yeah, another thing you could have done right here is sigma bond metathesis, where the palladium, where these electrons take the H, and at the same time the chlorine comes back to the palladium. So that's the sigma bond metathesis place as well. You could have done. All right, 6.11 has Grignard and copper 1. This is a good example of oxidation state not changing, but charge changing. Right. So what can happen here is copper 1 and the Grignard can do a transmetallation, where one metal exchanges stuff on a ligand. So this vanillic piece goes onto the copper, and since they're not really trading ligands, they're really just turning into a salt. So what it looks like is you have the magnesium with a plus charge, now the copper one with a negative charge with the ligand on the copper, right? So you really could say it's like a salt there. So the copper is copper 1. It didn't change oxidation state, but now it has a negative charge. And you could probably imagine, right, the actual negative electron densities on this ligand on the copper, the carbon. Copper likes to add in a Michael addition to alpha beta unsaturated carbonyls. A lot of times what it will do, it will sometimes form a 6-member ring transition state where you could say there's 1, 2, 3, 4, 5, 6. The copper kind of coordinates to the carbonyl. I didn't show it here, but you can imagine, right, a 1, 2, 3, 4, 5, 6 member ring transition where the copper delivers things into the beta position of an alpha beta unsaturated carbonyl system. Right, so it likes to get into that 6-member ring transition state. So it delivers that. Pi bond comes up. Again, it's like a migratory insertion, right? One ligand migrates onto another. Again, there's a couple ways you could do this, right? You could say the copper, essentially like a copper enolate now, right? This copper is bonded to the alpha carbon, but really the electron density is on the alpha carbon like an enolate would be. So let's have the copper just fall off. Electrons go there. So now you've remade, right? Copper 1 lost the charge, right? No longer has the charge. And now you've essentially made, right, an enolate that we've seen before. And then on workup, right, you add in water, and electrons would come down, attack there. And on water workup, you'd get the final product. All right, 6.16 for this one. You have a nickel 0. So one thing we have shown is that with pi systems, you can do oxidative additions. You can do some oxidative additions, and it's hard to know when. I'm not going to lie to you, it's hard to know when. So I would try to lead you and say, hey, do an oxidative addition on the pi system. Right? We try to tell you that. Right? Because if you looked at this, again, after I just got done saying, does this have any polar bonds to carbon? I would say no. Right? There's no carbon iodide, no carbon. There's no place. I look at this, and there doesn't seem to me to be a place to do oxidative addition. But we're going to do oxidative addition onto a pi system. So it's a little different. So you can do oxidative addition onto pi systems, but I would have to usually direct you and tell you, today, in this problem, I want you to do oxidative addition on the pi systems. Right, another good question is, right, really the nickel could just be like a Lewis acid here and have it coordinate and then just do a Diels-Alder. Right, because the final product is really just a Diels-Alder product. Right? So we could just do a Diels-Alder. But since it's organometallics, let's go ahead and try to use the metal a little bit more. But, so what happens first? So oxidative addition. It's a little different oxidative addition than you've seen. So this diene, right? One electron, one electron, one electron, one electron, one electron, one electron. So we're forming two new bonds to carbon, but not two carbons actually bonded together, right? So nickel is going to be bonded in the middle of these guys. So this is the oxidative addition here. Right, so the nickel ends up there. Now once the nickel's there, nickel 2, right, did oxidative addition, you can do migratory insertion, right, where one, and again, it doesn't matter which one I pick. I picked the inside one just because I felt like it'd be more crowded, but it really, right, if you wanted to, you could go this way first. It's up to you. So it doesn't really matter which way you go. So migratory insertion. Now we're back here. Nickel 2, reductive elimination. Get back to nickel 0, and you have your cyclic product. Again, you're given the product always in these things.
Oxidation.
So it was oxidative addition, migratory insertion, reductive elimination. Those are the 3 steps.
Did you replace the nickel with palladium 0?
You could replace the nickel with palladium 0 too. Yep. They just, I mean, just, yeah, you could replace it with a lot of metals. Or you could have just done it without a metal and done a Diels-Alder too. All right, working on 6.17. Now we have rhodium 1 and this kind of interesting alkene cyclopropane. And so I'm going to show you again here, we're going to do an oxidative addition onto a pi bond, right? So it's almost like forming like a, what we used to call the bromonium ion, right? But it's kind of with a metal, right? We're doing oxidative addition. So with rhodium 1, so we're going to do an oxidative addition. So the rhodium is going to end up bonded to either of these carbons, forming a rodeo cycle. Woo. And now I did number the carbons because this is hard. Right? If you don't number the carbons, we're going to do a rearrangement essentially. You can kind of call this a ligand substitution, but really it's a rearrangement. Because you could all probably guess, right? A 3-member ring with rhodium, probably not that stable. Rhodium is pretty big. A cyclopropane, right? Also, bond angles are terrible, right? So what we're going to do is we're going to pop open both of them. We're going to pop open both of them. So we're going to break rhodium carbon bond and break a carbon carbon bond and replace them. Right? So we're breaking 3 to 5. It's all fishhook arrows. So rhodium is not going to be bonded to 5, so 1 electron, and 2 and 3 are not going to have a pi bond between them. Not going to have a pi bond between them. So we're popping open this thing. So really it's a rearrangement. You can call it a ligand substitution. I don't care. You could call it a migratory insertion. It's messing around, right? So now we're back to something that's a little more reasonable, hopefully. Right, we have 1, 2, 3, 4, 5, 6. Usually rhodium likes to be in a 5-member ring, but 6 will work. Again, coordination, there's alkyne in the system. And here they were very careful about making it R and R, so there's no differential. Right, you could get 2 different products if they were different things. And it's a whole other level of complexity. We want to go there. Migratory insertion, 1 attacks. Right, we could have done with 5 first, doesn't matter. 5 could have done it first. I just chose 1. No difference. So migratory insertion. Now once we're there, we still have our rhodium 3. Now we need to do reductive elimination, which we've done before. And we have our 7-member ring. And our alkyne is added in. And we're back to rhodium 1. I found a way to turn these R's to E's. I promise they're the same thing. Don't fret at night about the R's to E's. There is no fancy reaction that turns an R to an E. Yet. So for 6.19, we're starting with palladium 2, and this is going to be one of those ones we want to turn palladium 2 into palladium 0. So how did I know to do that? Because I looked at my starting material and I said, oh boy, there's that carbon iodide bond. That means I want to do oxidative addition. Palladium 2 is more nucleophilic than palladium 0, is much more nucleophilic than palladium 2, right? Because palladium 2 is much more delta plus, it's 2 plus oxidation state, whereas palladium 0 has the lone pair. So oftentimes we'll buy palladium 2 salts that we turn into in situ into palladium 0. Now I showed you 3 ways. So one of the ways here, if you notice, right, there's always a mishmash of things in the system usually. So in this case, there's some triethylamine. We showed you this mechanism, how triethylamine could do this. Let's just talk through it. So triethylamine can attack and essentially do a ligand substitution on palladium-2. All right? So still palladium-2. There's our Cl minus floating around, right? There's a plus charge on the nitrogen, right? So that's a dative a coordinating bond there. But there's Cl minus floating around, so the charges balance out. We can do a beta hydride elimination, right? A beta hydride elimination, which then gets us to an H on the palladium, right? And now we can do reductive elimination with that. And we've created HCl, this salt from the beta hydride elimination, and now we're down to palladium 0. All right? So now that we have our newly formed palladium 0, we can do our traditional oxidative addition right into the polar carbon iodide bond. Now we have palladium 0 to palladium 2. Coordination, right? Usually it coordinates to the carbon of this carbon monoxide. Migratory insertion. I always, the product, so I know I want to migrate on, I don't want to put the iodide on there, I want to put the carbon on there. Yep, good point. The book has a mistake here. In the book, they forgot to put carbon monoxide. So, whoops. So you gotta, I didn't just add this out of nowhere. So in Grossman, this edition, hopefully future editions they fix this. There is carbon monoxide in 6.19, but they don't show that in the problem, but it is here now. So since it's here now, we're gonna use it.
They said you can create mass.
Yeah, it was there. So migratory insertion, carbon attacks, pi bond comes down, forms a real bond. It's a real bond. Just like you could be a real boy. All right. So now we have palladium 2 again. Now we know from the product we're gonna make a ring. We're gonna do a ligand substitution. Oxygen attacks, kicks out the iodide. Still palladium 2. I minus comes back in, or we also, right, there's also a lot of triethylamine, that initial thing that turned from palladium 2 to palladium 0. There's probably enough triethylamine to also, right, that's a better base than I minus. But. So now you have palladium 2. We're going to do that reductive elimination, which gets us to our cyclic product. Why is it? I am delayed.
It is like so Nagashi.
So 6.20. Again, you're going to want to turn palladium 2 into palladium 0, as in just like we did before. So there's some triethylamine in this case as well. So now once we have our palladium 0, you can do your oxidative addition. So now that we have our palladium 0, we can do that oxidative addition here. Once we do that oxidative addition, all right. Now we have the palladium in the bond. Within the ring, just remember here, there is a pi bond right there. Right, so just kind of rotate that around, and now we can do a coordination and a migratory insertion to that pi bond. So again, carbon attacks, pi bond comes up, forms a real bond with palladium for that migratory insertion. Now at this point, you should have your palladium bonded. So now once the palladium is on there, you always want to look, when you have these palladiums, to look for beta hydrides or things to do a beta elimination with. So in this case, there you have your H. Going to do a beta hydride elimination, make a pi bond, and then I'll actually give you your product in this case. All right, taking a look at 6.21. This is your classic Stille coupling. We actually start with palladium 0 here. First thing we'll do is a oxidative addition into that carbon iodide bond. Get to palladium 2. Within the same molecule, right? Just for simplification's sakes, I just did this as one big. It's a lot of stuff there, but really that's all. We're using this to form one big ring. So we do our oxidative addition. We have our palladium 2. Our palladium 2 then will do a transmetallation with the tin, swapping out the iodide on the tin, the carbon piece onto the palladium. Usually you want to put the carbon pieces on the palladium. Those are the ones, the palladium's where the action kind of happens. So then once we do that, after that transmetallation, we can do a reductive elimination. Palladium 2 goes back to palladium 0. We still have our tin iodide product. And we form our macrocyclic final thing. Look, we form the mushroom. There's obviously right stuff here. This is biology squiggly line. I was lazy. All right, back to palladium 0. For 6.22, again, starting with palladium 0, carbon-chlorine bond, right? Not as good as a carbon iodide bond as far as polarized, but we can still do oxidative addition in there. Palladium 2, this was a little different. We have a negatively charged nitrogen species, so like almost like LDA. So an amide, an N minus. So the N minus attacks the palladium, kicks out the chlorine. So that's just your old-fashioned ligand substitution, right? You can imagine the Cl minus be more stable by itself than an N minus. So kick that out. N minus, lithium plus. So there's Li plus. So when the Cl minus comes off, you're going to make lithium chloride, which will probably crash out of solution, so as a salt. Now you still have palladium 2, right? Oxidative addition, oxidation state didn't change. Do your reductive elimination. Back to palladium 0. Pretty straightforward.
Phosphorus terbutyl is just salt.
The phosphorus terbutyl, a lot of times there's phosphorus stuff, that's usually ligands. Different fancy ligands to put on the metals that I've failed to put on here. Right, they help. Usually there's phosphines on these that are maybe make the metal more electrophilic or sterically bulky. Right, there's someone took a lot of time to figure that all out, but it's really not affecting the mechanism what it is. All right, so again, we're starting with palladium 0. We have polar bond, O triflate bond, so that's what we're going to do an oxidative addition into. Get palladium 2. There's carbon monoxide in the system, so we're going to coordinate to the CO. Again, migratory insertion, pi bond comes down. Palladium does not change oxidation states. All right, so still palladium 2. There's a tin reagent in there, so we're going to do transmetallation of that first, or now we're going to do transmetallation. I mean, in theory, you could have done transmetallation first if you wanted to. That'd been fine. You could have done transmetallation first. So the O triplet is going to go on the tin. The carbon piece is going to go on the palladium. Now we have palladium 2. We're going to do a reductive elimination, right? And the silicon is going to be trans, right? Because it was a trans double bond here, right? So the palladium is going to stay on the same side as the tin was, so it's trans. That's like the last little bit. And we regenerate palladium 0, and we make our other tin product. Yep, so the highlighted point here that I didn't highlight enough, right? When you do this transmetallation, so the silicon and the tin were trans to start. So when the tin does a transmetallation, the palladium and the tin are also going to be trans. Or the palladium and the silicon, are going to be trans, right? If they were trans before the transmetallation, they need to be trans afterwards, right? So that's the key point here is that this trans double bond is going to stay a trans double bond throughout this reaction. Yep.
Silicon, is it strong enough acid to attack alkene?
No, the silicon is not going to be a strong enough acid to be attacked by an alkene. No, right? So the silicon already has 4 bonds, right? Silicon wants 4 bonds. It doesn't really have a good leaving group, right? In theory, you could have 5 bonds, but probably not.
Is there a situation when, like, instead of having a trans compound, like coordinating with the palladium, you would have something that's cis, and then like you would switch to trans?
If this started as cis,
yeah,
it would have stayed as cis,
okay.
right? If it started as cis, it would have stayed as cis. But isomerizing, that's a different thing. Turning a cis into a trans or trans to a cis, that's a different process. But if this was cis to start, it would have been cis in the product. All right, 6.24. Now in this one we have an epoxide, acetic acid, and palladium 0. So the first thing I'm going to do is I'm going to use the acetic acid, right, and have it protonate the epoxide. Right, so that's the first thing that happens. And then now this one's a little different. Again, you might say I don't see the carbon iodide, the carbonyl trifluoride, or the silicon H. But we've made this bond that much more reactive. So instead of just doing a straight SN2 with a palladium, right? Metals can do SN2s. So instead of doing straight SN2, we're going to do an SN2 prime, probably because of sterics, right? Palladium's pretty big, so it might be hard for it to just go directly attack that carbon. So instead, it's going to attack this pi bond on the back side, right? Those electrons move there, and then opens up the ring, right? But it's going to have to be, right? Anytime you attack on epoxide, there's always a trans addition. So it's still going to be trans. So it's still an SN2, but it's a different type of SN2. We call this an SN2 prime. So it's an oxidative addition in an SN2 prime sense. So instead of attacking the carbon of the epoxide directly, you attack something that's a couple carbons away. Yes?
Can you make the acetate group first?
So the O acetate group's not that good of a nucleophile, right?
Yeah, you can.
Because of resonance.
CO2 and methane to make the. No.
Nope, we start out with acetic acid. Acetic acid is just there to protonate it. So now we have our palladium, right? Notice the hatched. It came in SN2 style, but from farther away. We open up the ring. Now our O acetate can come back into a SN2, because now this is a much palladium 2 with a plus charge, right? So notice the palladium did an oxidative addition here, and then to balance my charge, who lost electrons? The palladium did. So the palladium got oxidized, and it also has a plus charge, right? Remember, formal charge is different than oxidation state, right? So palladium has a plus charge and is palladium 2.
Getting confused, Jeff.
Yep. And then the O acetate comes back and attacks SN, just regular SN2. Palladium gets the electrons back. So that's like a reductive elimination, essentially. The palladium's getting those electrons back. So now it's palladium 0, charge is gone, and the acetate's on the top. Right? So almost like SN2s can be both an oxidative addition or a reductive elimination. Depends on, right, if you're the group leaving, it's like a reductive elimination. If you're a group attacking, it's like an oxidative addition. You can think of it that way. So a good point. Another way you could draw this is by having essentially the palladium coordinate here, and then essentially do essentially slipping, where you have this as a allyl system, with the palladium sitting on the bottom of it. It has to be in the bottom, right? Because the palladium, right, has to break this bond, has to be in the bottom. But it would be, instead of doing like an SN2, it'd be more like the palladium coordinates, and then it slips, and it breaks that bond. And there's like that little circle there where it's palladium's taking up two coordination sites, and one of them's oxidizing it, one's an anionic site, and then the palladium eventually gets delivered, or the acetate would come from the top, and you get there as well. Just a little different way to do it. There's a couple ways you could do oxidative addition here.
And slip all the way around, kind of,
Kind of, yeah.
like washing around.
Yes,
No.
but it's always on the bottom face. So the
Okay.
key is the stereochemistry stays the same. I think it's just easier to see the stereochemistry with this way. All right, 6.25a, starting with palladium 2. Again, how do I know I need to use palladium 2, or do I need to turn it to palladium 0? In this case, again, I don't see any polar bonds, right? So really, palladium's acting like a Lewis acid, and usually if I need you to do like that thing with the nickel did, or an oxidative addition on a pi bond, I'll tell you. So here, oxygen attacks the palladium, ligand substitution, right? Still palladium 2. Acid-base reaction, the O acetate that fell off takes that H to make one acetic acid at first. At this point, we have a beta hydride. Beta hydride elimination from the palladium, still palladium 2. At this point, we could do reductive elimination to get back to make palladium 0, but we know the product, right? If we get the pi bond here, it'd be an aromatic system. So this is that isomerization you kind of talked about, like how can we move double bonds around? When you have a metal with an H on it, right, you can essentially change the double bond, the location of the double bond, this metal hydride. So it coordinates, the H goes there for a migratory insertion. Now the palladium's on the carbon here. We could do another beta hydride elimination. So palladium 2 the whole way. Now, we have an aromatic system because now the double bond is essentially moved from outside the ring to inside the ring. So the metal has allowed us to do that. And once we make the aromatic system, we're not going to mess with that, right? That's really stable. So now we have palladium-2, which is going to undergo reductive elimination. But that's a problem because we started out with palladium-2, not palladium-0. Right? Palladium-0 is not electrophilic enough to activate a pi bond, maybe, right? Palladium-2 is much more delta plus. It's already 2 plus. So then we have a co-catalyst. We have 2 copper 2s, right? 2 copper 2s, which are willing to take some of these electrons from palladium. So they take 2 of those electrons, make 2 copper 1s, and then make palladium-2, right? So these 2 electrons are gone now. The coppers took them because they went from 2 to 1. But then how do we regenerate the copper? Right, we add in O2, which can turn copper 1 into copper 2. It makes water, so we use actually oxygen to turn the co-catalyst over. And now we're back to palladium-2, which can go back to the product, or the start materials. All right, 6.25b. So again, palladium-2, there's no apparent place to do an oxidative addition, so the palladium-2 is just going to coordinate to our alkene. Also, in the final product here, this is a tricky one. All of a sudden, there's a new oxygen, and so that had to come from somewhere. And essentially, the only place it could have come from the reagents in the starting materials, that oxygen must have come from the water, right? So that's kind of the trick here is to recognize maybe that came from the water. So the palladium coordinates, activates the alkene. Water can then attack, right? The carbon, we know it ends up, right? We know the product. So it's a ligand substitution. We kick out the chlorine, which then can take the H, right? Because from the resulting plus charge, always balance our charges. Now at this point, we can do a beta hydride elimination, right? We know we need to turn this into a ketone, so let's do a beta hydride elimination. So we've made HCl before. Now we've made essentially an enol. Enols react with HCl to turn themselves into ketones. Right? It's a tautomerization essentially. Right? We regenerate HCl here. Right? If you do the thing, this H went to there. Palladium-2 then again can undergo reductive elimination, make some more HCl, which helps facilitate that tautomerization. Palladium-0, of course, is not what we want. We want palladium-2. Use the co-catalyst copper-2. 2 of those takes electrons away from the palladium, makes 2 copper 1s, which then gets oxidized by O2 back to copper 2, and we begin the cycle again.